Welcome to our video on L'Hopital's rule, which is used for finding the limits of indeterminate forms. L'Hopital's rule is an application of the first derivative to evaluating indeterminate limits of this form here. So this word indeterminate means that it can't be determined in the form it's in. So we're most likely interested in understanding how our function behaves, which is why we'd be taking the limit. Indeterminate forms may occur when you try to evaluate a limit by plugging in the x value that we're approaching in the limit. They're indeterminate because they violate or contradict some mathematical law or laws which govern real numbers. There are 7 indeterminate forms which are shown in the following table. You may use L'Hopital's rule in order to evaluate these limits. Some indeterminate forms can be evaluated using alternate methods that we have already learned, but L'Hopital's rule generally makes this an easier task. There are 5 determinate forms also shown in one of the following tables. The word determinate means that we can determine whether you have one of these answers as your limit by some other method that doesn't violate the laws of real numbers. We've done these in the past chapters. When we talk about indeterminate and determinate limits, we don't want to think of infinity as a knowable real number, so we can't assume that the real number arithmetic rules apply to infinity. So in this table, I've listed the 7 indeterminate forms which will use L'Hopital's rule, and I've described why they're considered indeterminate. So you want to go ahead and read through these explanations, which I've tried to make as understandable as possible. So I'm not going to go through and talk about all these reasons here on the video. So go ahead and read that on your own. So what I will say, though, about this table here is that these 2 forms, 0 over 0, plus or minus infinity over plus or minus infinity, are the forms that we want to get it into our function so that it looks like this quotient setup here. And these other 5 right here can be rearranged so that we have them in this form, and that's what we're going to work at. So we can say here that these 5 here need to be converted algebraically to either 0 over 0 or infinity over infinity so that we can use L'Hopital's rule. And that's part of what we're going to be working on here. So in this table here, I've listed the 5 determinate forms and the conclusion that you could make when you have one of these forms here. So we can actually make the conclusion by looking at this form here. These are called determinate forms. When you have these, you cannot use L'Hopital's rule because we cannot get it into the form that we need to apply L'Hopital's rule. So L'Hopital's rule says, suppose f and g are differentiable and g prime of x is not equal to 0 on an open interval I that contains a, except possibly at x is equal to a. So you could have a hole, for instance. Also, suppose that the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is also equal to 0. So this is one case. Or the other case is the limit as x approaches a of f of x is positive or negative infinity, and the limit as x approaches a of g of x is also positive or negative infinity. So this is the second case. So this means we have one of these indeterminate forms. This top one here, 0 over 0. This second one here, infinity over infinity. Then we can say that the limit as x approaches a of the quotient f of x over g of x is equal to the limit as x approaches a of the quotient f prime of x over g prime of x. Okay, and this last part here says if the limit exists, or it could be positive or negative infinity. So this is the statement of L'Hopital's rule. So there is a proof of L'Hopital's rule in your online textbook, but I'm not going to go through that at this point. So when you run into one of these indeterminate power forms here, or you've got some function in the power position and you're trying to take the limit of something that looks like this, we end up having to use natural logs in order to algebraically turn our setup into 0 over 0, or plus or minus infinity over plus or minus infinity, so that we can then apply L'Hopital's rule to our limit. And we're going to do some examples that need this technique. So let's jump into our example problems now. So our first example, we have a polynomial over a polynomial. So first we want to see if we have an indeterminate form when we try to evaluate our limit as x approaches 0. So I would have 0 squared minus 3 times 0. Well, that's 0 in the numerator. And then I would have 0 squared plus 2 times 0. That's 0 in the denominator. So that's 0 over 0, so I can apply L'Hopital's rule. All right, so that says that this limit is equal to the limit as x approaches 0 of the ratio of the first derivatives. So the first derivative of the numerator is 2x minus 3. The first derivative of the denominator is 2x plus 2. Now, you have to be very careful that you're not actually taking the derivative of this as one function like you would a quotient rule problem. You treat this as a separate function and this as a separate function, and you're writing the first derivative of this on the top and the first derivative of this on the bottom. So it's a very different thing that we're doing here. This is not the quotient rule. All right, now I try to evaluate the limit this time and see what I get. So if I put 0 in at this point, I want to check and see if I can evaluate it. So that's equal to negative 3 over 2. So L'Hopital's rule says that this is indeed my limit. So now I stop. I've got my answer. So in example 2, I want to check and see if I have one of the indeterminate forms. So I'm approaching 0, so I evaluate this limit at 0. 2 times 0, which is 0, so that's, just write that down, 0 minus the sine of 2 times 0, which is the sine of 0, so that's also 0. And then I've got 0 here, plus the sine of 0 again, which is also 0. So I've got 0 over 0. So that means I can apply L'Hopital's rule. So now I want to take the first derivative of the top line and the second line separately, the top function and the bottom function separately, and try to evaluate that limit. So I'll have 2 minus, that would be the cosine of 2x, chain rule, times 2. That would be 1. And this would be same situation, cosine of 2x times 2. And now I try to evaluate this limit as x approaches 0. So I'll get 2 minus 2 times the cosine of 0, and 1 plus 2 times the cosine of 0. So that's 2 minus 2 times 1, 1 plus 2 times 1. So that's equal to 2 minus 2 over 1 plus 2, which is 0 over 3, which is 0. So those are real numbers, so real number laws apply, so this limit is actually 0. So employing L'Hopital's rule, we were able to arrive at a limit of 0. So in this example, we're evaluating the limit as x approaches infinity of the natural log of x over x. So the natural log function goes up rather slowly, like this. So it approaches infinity as x approaches infinity. So infinity, in the numerator, we're approaching infinity. And then it says x approaches infinity, so we have infinity in the denominator as well. So in this form, this is one of our indeterminate forms, so we can use L'Hopital's rule. All right, so that means this is the same as the limit as x approaches infinity of the first derivative of the natural log of x, which we know is 1 over x, divided by the first derivative of x, which is 1. So this is just the limit as x approaches infinity of 1 over x. All right, so now we already know how to evaluate a limit such as this. When you've got a fixed number, so that number is not growing or shrinking or anything, it's staying a 1, but this number is growing extremely large. So that means this limit is approaching 0. So we can conclude that this limit is approaching 0. In this example, it says, evaluate the limit as x approaches 0 of the sine of 5x divided by 3x. So if we think of substituting 0 in here, we've got the sine of 0 divided by 3 times 0. So we have 0 over 0, so that means we can apply L'Hopital's rule. All right, so that means this is the same thing as the limit as x approaches 0 of the first derivative of the sine of 5x. That would be the cosine of 5x, chain rule, times 5 divided by 3. So if I try to evaluate this limit as x approaches 0, I get 5 cosine of 0 divided by 3. So that's just 5 times 1 divided by 3, which is 5/3. Right, so we've got a limit of 5/3 using L'Hopital's rule. So looking at this one here, we want to see if we have an indeterminate form. That would be step 1. So the limit as x approaches pi over 4 of secant of 2x times 1 minus the tangent of x, what does that approach as x approaches pi over 4? So we can write that as the limit as x approaches pi over 4 of 1 minus the tangent of x divided by the cosine of 2x. And this is because the secant of x is equal to 1 over the cosine of x. So I'm putting the cosine in the denominator. So now let's take a look at substituting pi over 4. Tangent of pi over 4 divided by the cosine of 2 times pi over 4. So that's 1 minus, so pi over 4 is right here where we've got root 2 over 2, root 2 over 2 for the sine and the cosine. So remember the tangent is sine over cosine. Well, if they're the same value, in this case your tangent will be 1. So we've got 1 minus 1 in the numerator, and then we've got the cosine of pi over 2. That's here, so the cosine is 0. So we've got 0 in the numerator, and we've also got 0 in the denominator. So that means we can apply L'Hopital's rule. So from this point, we want to find the first derivative of this and the first derivative of this. So we can say this is equal to the limit as x approaches pi over 4 of derivative of 1 is 1. So this would just be minus the secant squared of x. And the derivative of the cosine is the negative sine of 2x times 2 using the chain rule. Right, so those negatives are going to cancel. So this gives me the limit as x approaches pi over 4 of the, let's put that secant down in the bottom there. So this would be 1 over the cosine squared of x. Then we've got that 2 out in front, sine of 2x. All right? Now let's try to evaluate this by substituting pi over 4 and see what we get. So this will give us 1 divided by 2. So the cosine of pi over 4 we said was root 2 over 2. So that means I've got the cosine squared. And then I've got the sine of 2 times pi over 4, which is pi over 2. Right, so we've got 1 over 2 times root 2 times root 2 is 2. 2 times 2 is 4. The sine of pi over 2 would be 1. So that leaves us with 1 over, that would be 4 over 4 times 1, which is 1 over 1 times 1, which is 1. That's 1. All right, so we were able to evaluate this limit using L'Hopital's rule, and the limit is 1. All right, so now taking a look at this example, I've got the limit as x approaches 0 from the plus side, from the right, of x times the natural log of x. So if I try to substitute 0 into that, we want to see whether we can get an indeterminate form. So that's 0 times the natural log of 0, the limit of the natural log of 0 as we're approaching it from the right. So I've inserted this little picture here so that you can see what that limit is. As I'm approaching it from the right, it approaches negative infinity as the closer I get to 0 from the right. So that means I've got 0 times negative infinity. This is this indeterminate form here. So we want to try to convert that into 0 over 0 or infinity over infinity so we can apply L'Hopital's rule. So this means we need to get it in quotient form. So the technique we use to do that is we say this is the same thing as the limit as x approaches 0 from the right of ln of x divided by 1 over x. So you can see that if you flipped and multiplied, you would go back to the original form. So this is an equivalent form to this. This allows us to get something in the numerator and something in the denominator here to algebraically manipulate this into one of the indeterminate forms, 0 over 0 or infinity over infinity. So now, as we know, we already said that the limit as x approaches 0 from the positive side of the natural log of x is negative infinity. So that's what I have in the numerator. Now, if you approach 0 in the denominator, and this is a fixed number, you can see that as this number becomes extremely small, that this is going to approach infinity. And we've already talked about that in other problems that we've had before. So now I can apply L'Hopital's rule in this form. And I have to use this setup right here where I'm going to take the first derivative of this and the first derivative of this. So now I can say this is equivalent to the limit as x approaches 0 from the positive side of 1 over x. That's the derivative of ln of x. And remember, this is same thing as x to the minus 1. When I differentiate that, I get negative x to the negative 2, which is negative 1 over x squared. So I have negative 1 over x squared. So now, if I rewrite that, I've got the limit as x approaches 0 from the positive side of 1 over x. So I flip and multiply. That's times negative x squared over 1. That's equivalent. So that can be reduced to negative x over 1. All right, so I've got negative x over 1, so I'll just leave the 1 off. So I can take the limit as x approaches 0 from the positive side of negative x by substituting 0. So I just have 0. So my limit is 0 by L'Hopital's rule. So now this one says evaluate the limit as x approaches infinity of x to the fifth e to the minus x. So I want to see whether I can apply L'Hopital's rule if I have one of the indeterminate forms. All right, so this can be written as x to the fifth times 1 over e to the x. Bring that negative means move e to the x down to the denominator. So this is x to the fifth divided by e to the x. So if I say what happens as x approaches infinity, I can see my numerator is going to approach infinity, and e to the infinity, that will also approach infinity. So just recall the e to the x function approaches infinity in this fashion. As x approaches infinity, e to the x approaches infinity. Of course, as x approaches negative infinity, e to the x approaches 0. All right, but we have this side of it here. So because we have this indeterminate form, we can apply L'Hopital's rule to evaluate this function. All right, so this will be the same as the limit as x approaches infinity of x to the fifth over e to the x. So I'm going to take the first derivative of both of those. So I'll get 5x to the fourth divided by e to the x. So notice that this is still infinity over infinity. So I'm going to apply L'Hopital's rule again. So this is the same thing as the limit as x approaches infinity of 4 times 5 x to the third this time over e to the x. If I've evaluated, I'm going to still have infinity over infinity, so I'm going to apply L'Hopital's rule again. So this is the same thing as the limit as x approaches infinity of 3 times 4 times 5. This time I'm down to x to the 2 over e to the x. Well, I've still got infinity over infinity, so I'm going to do it again. And you can keep going as long as what you arrive at when you take the derivative can still be evaluated using L'Hopital's rule another time. All right, so now I'm going to multiply by 2, and I'm down to x over e to the x. So I'm still going to get infinity over infinity, and you can see one more time I have that. All right, but this time when I take the derivative, that x is now going to be a 1. First derivative of x is 1. So I've got 2 times 3 times 4 times 5 times 1, which I won't write, over e to the x. All right, so now I can evaluate this limit. It's not indeterminate anymore. This is going to be some number here, which is going to be some fixed number in the numerator. However, this number in the denominator is going to approach infinity. It's going to grow without bound. So whenever you've got a fixed number that's not changing divided by a number that's increasing without bound, your conclusion is that your limit is 0. So I've evaluated this limit by applying L'Hopital's rule as many times in a row as was valid until I could evaluate the limit, until I had a determinate form. So my limit was 0. Right, so for this example here, it says I've got the limit as x approaches 0 of, from the right side, of x to the 8x power. So we're going to take natural logs of both sides and use algebraic manipulation to get this limit into the form where L'Hopital's rule applies. All right, so the way that you do that is that you first say that you're going to call your setup y. Y is the limit as x approaches 0 from the positive side of x to the 8x. That's your y. Now I'm going to take the natural log of both sides. Everything goes inside those brackets there. And now, according to the laws of limits, I can take that limit outside and call this ln of x to the 8x. So the limit and the natural log are able to switch places. All right, so now I'm taking the limit of the natural log of x to the 8x, which we can rewrite as the natural log of y is equal to the limit as x approaches 0 from the plus side of 8x in front now, according to the power rule of logs, ln of x. All right, so now let's check and see whether I've got one of the indeterminate forms when it looks like this. So if I evaluate this as x approaches 0 from the right side, this would just be 0, 8 times 0, so I've got 0. And if I evaluate the ln of x, that's what I put this graph over here for, as x approaches 0 from the right, the limit of that is negative infinity. All right, so this is one of my indeterminate forms according to the first table I showed you, but we need to convert it to one of these forms in order to use L'Hopital's rule, and we can do that. So this is the same thing as the ln of y is equal to the limit as x approaches 0 from the positive side of the natural log of x divided by 1 over, let's put the 8 up here, 1 over x, like we did in that other problem. So this is the same thing written a different way. This and this are equivalent. Flip and multiply, and you can verify that this is the same thing. So now let's see what we have. So in the numerator of 8 times negative infinity, well, that'll still be negative infinity, over 1 divided by a very small number as we approach 0 from the plus side. So remember, fixed over something very small will approach infinity. All right, so this is one of the forms that is legal to apply L'Hopital's rule. All right, so now we're going to apply it, which means I'm going to take the derivative of the numerator and write it over the derivative of the denominator. So ln of y is equal to the limit as x approaches 0 from the right. So 8 ln of x, the derivative of that would just be 8 over x, because remember the derivative of the natural log of x is equal to 1 over x. That's my numerator. And then the derivative of x to the minus 1 is negative 1 x to the minus 2, which is negative 1 over x squared. So I can fix this up a little bit. So this is the same thing as 8 over x times, flip and multiply, negative x squared over 1. That's the same thing as negative 8x. All right, so now what I have is the natural log of y is equal to the limit as x approaches 0 from the right of negative 8x. All right, so now I can substitute 0 into there. I'll have now a determinate form. So this is negative 8 times 0, which is just 0. All right, so what I have now, I'm not done yet, the ln of y is equal to 0. But I'm really after y. Y is this. I want to evaluate that. So I need to solve for y, which is easy enough to do in this case. So if I raise both sides by e, I'll have y is equal to e to the 0, which is 1. So my limit is 1. So my conclusion is that the limit as x approaches 0 from the positive side of my original function, which was x to the 8x power, is equal to 1. Using L'Hopital's rule and algebraic manipulation of the ln form. All right, so this is a very powerful technique. So this example says, evaluate the limit as x approaches infinity of 1 plus 1 over x to the x power. So I've got an x in the power position again. So I'm going to take the natural logs and use algebraic manipulation to get the limit into the form where L'Hopital's rule applies. All right, so first I say y is equal to the limit as x approaches infinity of 1 plus 1 over x to the x power. Then I say ln of y, ln of both sides, ln of the limit as x approaches infinity, 1 plus 1 over x to the x power. All right, then because of my limit rules, I can switch places here, and I'll have the ln of 1 plus 1 over x to the x power. And then because of our log rules, this is the same thing as the limit as x approaches infinity of x ln of 1 plus 1 over x. All right, so now I need to get this in the form of either 0 over 0 or infinity over infinity. Okay, right now I can see that it's not in the quotient form, but since I've done this on another problem, I know that I can rewrite this as the limit as x approaches infinity of, let's keep the ln of 1 plus 1 over x in the numerator and put 1 over x in the denominator, which is the same thing as having x in the numerator. Right, now let's check and see if we have one of the indeterminate forms now. So as x approaches infinity, I'm approaching 0 right here, and I'm approaching 0 right here. So I've got the ln of 1 in the numerator and 0 in the denominator. So if I look at ln, it crosses at 1. It's got an x-intercept of 1, 0, So we know that about the ln of x function. All right, so that means I have a 0 in the numerator and a 0 in the denominator, so I can use L'Hopital's rule. All right, so now I've got the ln of y is equal to the limit as x approaches infinity of the derivative of the numerator in this form. So I don't want those zeros there. Let's move that. All right. So the derivative of the natural log of 1 plus 1 over x would be 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x. Derivative of 1 would be 0. So the derivative of x to the negative 1 is negative x to the negative 2. Right, that's the numerator. And then I've got the derivative of 1 over x in the denominator as well, which is negative x to the negative 2. All right, so I can cancel those out. Those will cancel. All right, so now I'm left with the natural log of y is equal to the limit as x approaches infinity of 1 divided by 1 plus 1 over x. All right, so now if I try to evaluate this as x approaches infinity, I'll see that this will go to 0 because I have a fixed numerator and a denominator getting infinitely large, so this will approach 0. So I'm approaching 1 over 1, which is 1. So now I have the natural log of y is equal to 1. So I really need y, so I have to say e on both sides. Raised by base e, both sides, I'll get y is equal to e to the first power, which is e. All right, so my conclusion is that y is equal to so let's rewrite that. I don't mean y, I mean whatever y is, which is way back at the top. The limit as x approaches infinity of all that stuff. So by L'Hopital's rule, our limit is e. So here's our last example here. So this one says evaluate the limit as x approaches 0 of 1 plus sine 7x to the 1 over x. All right, so we've got this in the power position again. We're going to use the natural log approach. So we want to get it into one of our forms, either 0 over 0 or infinity over infinity, so that we can apply L'Hopital's rule. All right, so we know we're going to have to start by saying y is equal to the limit as x approaches 0 of 1 plus sine 7x to the 1 over x. Then we take the natural log of both sides. Sine is 7x to the 1 over x, like that. Then we switch places. The limit and the natural log. Now let me just make sure that you guys know that you don't want to take shortcuts in how you rigorously write out all these steps right here. All right, in order to keep to our mathematical language intact and correct. All right, so I'm going to write it out just like this. All right, so then I'm switching places here with the limit and the natural log. So I've got 1 plus sine of 7x to the 1 over x. All right, so now I've got the natural log of y is equal to the limit as x approaches 0 of 1 over x. Natural log of 1 plus sine of 7x. All right, so that can be written with this x underneath, and it'll already be in a quotient format. So this ln part is your numerator, and the x we can put down here as the denominator. That's an equivalent form. All right, now let's see what we have. So if we approach 0, we'll have the ln of 1 plus the sine of 0, which is 0. Remember we said the ln of 1 is 0. All right, so the ln of 1 is 0, where this is the ln of x graph. All right, so that's the natural log of 1 we said was 0. So 0 in the numerator, and then, of course, 0 in the denominator. So this lets us use, this says L'Hopital's rule applies. All right, so now we've got to take the derivative of the numerator and the denominator. So derivative of the natural log is 1 over times the derivative of the part underneath. So that would be 0. This would be 7 cosine of x. So I can say 7 cosine of x in the numerator. Chain rule. All right, though that's the derivative of the numerator. The derivative of the denominator is just 1. All right, so I don't have to write that. All right, now let's see if we can evaluate this as x approaches 0. So that would be 7 cosine of 0 divided by 1 plus sine of 7 times 0, which is 0. So this part is 0. This part is 1. So that means 7. All right, so I was able to evaluate the limit. So now I know that the natural log of y is equal to 7. All right, so I'm looking for y, so I have to say e. So y is equal to e to the 7th power. All right, so y, my original y, of course, was way back here. That was the limit of all that stuff. So I can conclude. So here it is. So once again, L'Hopital's rule allowed us to evaluate a limit which was otherwise pretty difficult to figure out with other techniques. All right, so this is these are all the examples we're going to do here. You have enough to get started on your homework and to try your hand at solving some of these types of problems. All right, let me know if you have any questions.